A data engineering team evaluates 6 open-weight models over 3 weeks. They run benchmarks, compare leaderboard scores, release papers, and debate architecture choices. At the end of 3 weeks, they select the model with the highest aggregate benchmark score. 3 months into production, the model is producing responses that are technically accurate but structurally unusable for their downstream application. The model was optimized during training for open-ended reasoning tasks. The application needed structured JSON output with consistent field names on every response. The benchmark they trusted did not measure that. The 3 weeks evaluation measured everything except the one thing that mattered for their use case. This article is the evaluation framework they did not have. This is Open Source Model Selection, In-House, Part 9. There are dozens of models available. Most of them are not the right choice for what you are building. Section 1. What open-weight model actually means for selection. Part 2 introduced the distinction between open weight and open source. It matters again here in a different way. When you select an open weight model, you are making 4 decisions simultaneously, not one. You are selecting a capability profile, the tasks the model handles well. You are selecting a hardware requirement, the minimum infrastructure needed to run it. You are selecting a license, the legal terms governing how you can use it and modify it. You're selecting an ecosystem, the community, tooling support, and update cadence that surrounds the model family. A model that scores highest on general benchmark but carries the restrictive license for your use case is not the right model. A model with excellent structured output performance that requires hardware you do not have is not the right model. Selection that ignores any of these 4 dimensions produces a decision that looks good on paper and fails in practice. Section 2. The current landscape in plain language. 5 models dominate practical open-weight deployments in 2026. Each has a distinct profile worth understanding before comparing benchmarks. The Llama 3 family from Meta is the most widely deployed open-weight foundation in production systems. The 8 billion parameter instruct variant is the default starting point for most first deployments because the ecosystem support is mature. The tooling comparability is broad and the license permits a commercial use for most organizations. The 70 billion parameter variant delivers frontier adjacent performance, but requires hardware at or above mid-range tier from Part 3. Llama 3 performs well across general reasoning, instruction following, and conversational tasks. It is a reliable default when the use case does not strongly favor another family. The Mistral family from Mistral AI offers 2 distinct architectural approaches worth distinguishing. Mistral 7B is a dense model that punches above its parameter count on reasoning and coding tasks and carries an Apache 2.0 license, the most pervasive commercial license in the open-weight landscape. Mixtral 8x7B is a mixture of expert models that activates roughly 13 billion parameters per forward pass despite having 47 billion total parameters. For teams that need higher capability without proportionally higher hardware requirements, Mixtral offers a meaningful efficiency advantage. The trade-off is serving complexity. Mixture of expert models requires more careful infrastructure configuration than dense models of equivalent active parameter count. The Qwen 2.5 family from Alibaba has emerged as the strongest performer on structured output tasks among the accessible open-weight models. If your pipeline requires the model to produce consistent JSON, extract entities into defined schemas, or generate output that downstream systems parse programmatically, Qwen 2.5 warrants serious evaluation. The license permits commercial use without attribution requirements that are less permissive than Apache 2.0, but are acceptable for most production deployments. For the NOAA pipeline in this arc, where structured extraction of event entities and relationships is a core requirement, Qwen 2.5 is the model that earns the closest look. The Gemma 2 family from Google and the Phi 3 and Phi 4 families from Microsoft occupy the efficiency end of the landscape. Both prioritize capability per parameter rather than performance at large sizes. Gemma 2 9B delivers performance comparative with large models from other families on many benchmarks while fitting comfortably on minimal viable hardware. Phi 4 from Microsoft has produced results that challenge the assumption that sub-10 billion parameter models cannot handle complex reasoning tasks. Both licenses, with specific use restrictions, require review before production deployment. Google's Gemma terms restrict certain high-risk applications. Microsoft's Phi license has provisions around responsible AI use that are worth reading carefully for regulated domain deployments. Section 3. What benchmarks actually measure. Benchmarks are the primary tool for comparing models before deployment and the primary source of selection errors. A benchmark measures model performance on a specific set of tasks under specific evaluation conditions. The most commonly cited benchmark in the open weight landscape measured general reasoning, mathematical problem solving, coding ability, and multiple choice question answering. These are valid measurements of the capabilities they target. They are not valid measurements of performance on your specific use cases unless your use case closely resembles those tasks. MMLU, Massive Multitask Language Understanding, measures performance across 57 academic subject areas using multiple choice questions. A high MMLU score tells you the model has broad factual knowledge and can select correct answers from provided options. It tells you nothing about whether the model produces consistent structured output, handles domain-specific vocabulary correctly, or generates responses that fit your application's requirements. Human Eval measures coding ability by asking models to complete Python functions from docstrings. Useful if your pipeline involves code generation, not useful if it does not. MTBench and similar instruction following benchmarks measure how well models follow multi-turn conversational instructions, more relevant for conversational applications than structured extraction pipelines. The benchmark that most directly predicts performance on the NOAA pipeline in this arc does not appear on most leaderboards. Structured output reliability, the percentage of responses that conform to a defined schema without requiring retry or repair, is measured in the median article referenced at the start of this arc and is not a standard leaderboard metric. That gap between what the leaderboard measures and what production pipeline requires is the reason benchmark-driven selection fails in practice. Section 4, the evaluation framework. Model selection for a purpose-built pipeline follows 4 steps in order. First, define your primary task type precisely. The NOAA pipeline requires structured entity extraction, semantic similarity matching for retrieval, and natural language generation for query responses. Each task type has a different model performance profile. A model optimized for conversational instruction following may underperform on structured extraction relative to its benchmark scores. Second, filter the hardware constraint. Eliminate any model that does not fit your available hardware at a comfortable utilization level. A model that maxes out your GPU memory leaves no headroom for concurrent requests or context window expansion. The hardware tier from Part 3 is your filter, not a preference. Third, filter your license. Identify your deployment context. Internal use only, commercial product, regulated industry, and match it against each model's license terms. Apache 2.0 is the most permissive. Meta's Llama license permits commercial use below a monthly active user threshold. Gemma and Phi licenses have specific restrictions. If a model's license creates legal uncertainty for your deployment context, eliminate regardless of performance. Fourth, evaluate your actual task. Take the models that survive the first 3 filters and run them against a representative sample of your real data. For the NOAA pipeline, that means a sample of storm event records with known correct outputs. Measure structured output conformance, entity extraction accuracy, and response quality on real queries. This evaluation takes hours, not weeks, and produces results that are directly predictive of production performance. Section 5, the selection for this arc. The NOAA pipeline has 3 requirements that drive the selection decision. The structured extraction tasks favor Qwen 2.5. The hardware profile of the minimum viable tier from Part 3 accommodates both Qwen 2.57b and Llama 3.18b comfortably. Both carry licenses that permit the use this case arc builds towards. The assembly article in Part 16 makes the final opinionated choice with full reasoning. The evaluation framework above is what makes that choice defensible rather than arbitrary. A selection you can explain in terms of task requirements, hardware constraints, and license terms is an architectural decision. A selection based on leaderboard position alone is a preference. Next, commercial self-hosted models when the open weight path is not the right call, and what the commercial self-hosted landscape actually offers in 2026.